Okay, so what we're going to look at now is some electrochemistry. Last time we did go over some review of um, oxidation and reduction reactions, which are the basis of electrochem. And let's see, where's my thing? Oh, here. So there is a video on that in case you need to review it um, over here. And the problem sets for this are all pretty much connected to one document that I keep repeating here, and there's already a key up for it as well on our website. So as you're working through stuff, you can kind of get a sense of it. So today I'm going to try to explain to you about what are known as voltaic cells and how they work. And really, this is the basis of chemical batteries. It's kind of interesting. And I'm going to start with just a little simple explanation and a couple demonstrations on the video. So what we're calling electrochemical cells, this type of cell is called a voltaic cell. Oop, another customer. And the way it works is it uses a redox reaction to produce electricity. So this is one of the major areas of electrochemistry is using chemical reactions to generate electricity. And this is what we're going to look at now. So let's look at a simple oxidation reduction reaction happening in a beaker. Oops, I forgot. I have so many things open, I don't even know what I'm clicking on anymore. So here you have a piece of zinc metal placed in a copper sulfate solution. Looks like it's pretty concentrated too because of how dark the solution is. And this might be time-lapsed. I'm not really sure because it goes pretty quick. Oh, it's not letting me open it up. Did I just freeze? Oh, of course. There we go. Okay, so as you watch, the zinc metal has like a silvery color, but you see this reddish material starting to form on it. And you also notice that the solution color is starting to fade. Well, that reddish material is copper. So the copper metal is coming out of the solution and kind of plating onto the piece of zinc, but the zinc is also dissolving at the same time. So this shows us a very straightforward, what we used to call single replacement reaction. Okay, but it is a redox reaction. I want to write it out for you so you can see what's going on. So, oopsie, in this case, what you just saw was zinc as a solid reacting with copper, I think it was copper sulfate in solution, and the products were zinc sulfate in solution. And then copper metal coming out as a solid. So let's show why this is a redox reaction, and let's show it as a net ionic equation anyway. So as a net ionic equation, you have zinc, which is neutral at first, interacting with copper ions in solution. And then you get zinc in the solution and copper coming out. So how is this redox? Well, you should be able to see that through a spontaneous chemical process, it seems like what this is suggesting is electrons are being lost by zinc and gained by copper. So as the zinc is losing its electrons, the copper is becoming neutral and the zinc is becoming charged. And if we wanted to write this as half reactions, we could say, okay, the zinc is becoming zinc ion and 2 electrons, and that, of course, is an oxidation because it's a loss of electrons. And then finally, the copper ions are picking up those electrons to become copper metal, and so the copper is being reduced. So there's the redox part. So when we talked about this earlier in the year, we never talked about really the energetics of this, like what's really driving this change. We just talked about some vague ideas that, oh, that one has a stronger attraction for the electrons than the other. But there's a whole way we measure this and can actually see it quite easily. So what's interesting is that if you take this system like we just saw it in the beaker, the energy is basically going to turn into heat, and you're going to get the chemical conversion and you'll get the products. What we want to do is tap into that energy flow. But how? How can we take this reaction and get in between the parts so that we can catch the flow of the energy? Let me give you an analogy that sounds really stupid, but I think is effective. Okay? So let's say you have a dog. I can't draw. That's my dog. Okay? Whatever. And you put that dog in his house and you give him a bowl of food. What's the dog going to do? He's going to sit there and eat the food. Okay, no big deal. But what if you took the dog and you put his food over here? He still wants to eat, right? But what does he have to do to eat? The
He has to
dog?
walk to it.
Yeah, he's going to have to go to it. Now, what if we happen to tie some load that we want the dog to carry for us? Couldn't the dog kind of do our job and say, oh, I'm hungry, and the dog walks and he carries the box along and does the work for us? So that's my analogy. The question is, how does that fit into this reaction? Well, we know that in this chemical system, when it's in one beaker, the copper ions want these electrons and the zinc gives them up. And as long as they're right next to each other, we can't really get in between. We can't get anything useful out of it. But what if we could separate the two reactions and force the electrons to move through something to get from A to B? Then we could use their flow to do work. And that's exactly what we're going to do. We're going to create what's called an electrochemical cell. But how are we going to separate this? What does that even look like? What does that even mean? So what we basically have to do is separate each of these half reactions, right? Because remember, these are half reactions in their own containers. So imagine if I did something like this. What if I took and made two separate beakers? And I'm going to draw this a little weird at first, just so you'll see why. And in one beaker, I put some liquid and I put a piece of metal. Let's put the zinc metal here. And in here, let's put a solution of zinc. So let's just put some zinc sulfate. And then on this side, I put my copper metal as a piece of metal on this. And then here I put some copper sulfate solution. So right now, if I did it like that, these two systems are not in contact, right? Like they're completely separate containers. But what if I attach something from one of these pieces of metal to the other? And I'm just going to put a little circuit here, just a little generic circuit here to measure the voltage. Well, if they're in contact, now there is a path for the electrons to leave the zinc and let more zinc. And you know what? Just for simplicity, I'm going to do this in net ionic form for a moment. And I'm just going to put the ions down here just to make it more clear what I'm saying. So what if we set this up? Now if the zinc ions here, or the zinc atoms here, give up electrons, they can travel toward the copper through the metal and toward those ions that want those electrons. The problem is, if you've done any electricity like in physics, you'll know that you need a complete circuit. So right now we're kind of missing the one path. We've got one way to go, but we need to complete the circuit. And so we're going to have to build something across this side too. And the reason for this is we need a way for the electrical charge to continue to flow. Otherwise the circuit stops. But my point is, if we did something like this, and this is what we're going to get into, is how does this actually look, how we do this. If we did something like this, we could actually tap into the energy that's pushing these electrons, and that's just an electrical current. It's a circuit now. And we could put something here other than a voltmeter or something like a light bulb, let's say, or your phone, and that flow of electricity, which is being driven by the chemical reaction, can be now used to do some kind of work. That is, in theory, the essence of these cells. And it's the basis of all chemical batteries, really. So the question now is, what are the details? How does this look? How do we do it? What do we measure? How do we calculate? All that stuff. So let me kind of get into one that looks real, and then I'll get into a simulated one so we can really understand it. So I picked another video that's this same reaction broken out the way I just described it. Here's what it looks like. So we're going to assemble this cell. You have your zinc metal and you have your copper metal. This is something called a salt bridge, which I'll describe in a moment. But watch how this is put together. So we have our solutions of zinc and copper sulfate, one in each separate beaker. Oops, keep trying to. I don't know why YouTube's acting funny to me now. Okay. We connect each of those metal electrodes, as we're going to see they're called. And this is just so we can put them on the meter so we can measure how much electricity they generate, really how much voltage. Okay. Now we're going to take those and put them into the beakers of solutions. Oh, for heaven's sake, can you just get to the point? All right, so here's the basic setup now. Let me pause this. So right now we have our solutions. We have this bridge that's basically filled with a solution, which I'll describe in a moment. And then we're going to put our electrodes in. The zinc one is going to go in the zinc solution, and the copper one is going to go in the copper solution. And when that happens, watch this meter. So we immediately are reading almost 1.1 volts. Just completing this circuit and putting this together, there is a driving force of electrons being pulled from the zinc toward the copper solution that is generating this electricity. And the electricity is passing through this meter, which again, instead of a meter, we could have a light bulb there and we could light the light bulb by the chemical reaction generating the electricity. This is the essence of a chemical cell. These are two half cells that, once put together, allow the redox reaction to happen. But it's their separation that lets us tap into the flow of the electricity. Now let's actually start breaking this down and seeing how do we figure all this out. So I'm going to build what's called a Daniell cell. It's based on the zinc-copper reaction. And I'm going to show you how we do everything about this one cell. So I want to just focus all my attention on this single example today, because this will be the one we hang everything else on. If you understand this one, everything else is just changing the reactions. So let's start with the actual cell. Now, when we build the cell, we are going to do it in such a way that there are certain key terms you need to know. So the metal pieces that we're putting in is going to be what's known as an electrode. When we make the electrodes, there's always going to be one that's going to be the negative terminal and the one that's going to be the positive terminal, kind of like on a battery. For voltaic cells, which are the kind we're talking about today, the anode is going to be the negative terminal, and the anode is going to be where the oxidation reaction occurs. The positive terminal is going to be the cathode, and that's where the reduction reaction occurs. That's one of the most important things to take away from today. Just remember this mnemonic: An-ox, red cat. Anode, no matter what kind of cell we do, is always the oxidation. The cathode is always where the reduction reaction occurs. Okay? Now, when we build this cell, which we're going to do now, I have to be careful so that my voltage reading comes out correct. So based on the reaction that we're going to use, the copper and zinc cell, we said a moment ago that it was the copper that's getting reduced. So this is the reaction we expect to be happening at the cathode. And then in this, again, this specific cell we're going to do, the zinc is being oxidized. So that should be what's happening at the anode. Now you'll notice that on my voltmeter here, the thing that's going to measure the voltage, there's a negative terminal, which is the black one, and there's a positive terminal, which is the red one. If I get this wrong, if I put them in the wrong place, it's just going to give me a negative voltage. It's just going to be signed for reversal. Not a big deal. But let's see if we can get it right. Since the positive terminal is the cathode, that's where we want the reduction. So it seems like we should put the copper here and put it in the copper solution. The metals on this side, we want to use the zinc as the electrode. So here's the cathode now, or no, the anode, sorry, I'm backwards. This is the anode. And then the solution is the zinc solution. Now, in the salt bridge, which is this thing across the in between, we need some ions to act as a conducting solution. Remember, electrolytes, we said, conduct electricity. So we have to pick something that itself is going to be very non-reactive. So the salt bridge, which is kind of that U-tube. So this is what I thought what a U-tube meant when I was a kid. U-tube for me was that, not what you think. So the salt bridge is going to just usually have some kind of conducting solution. And most of the time, we're going to use a nitrate or a sulfate of some salt. So like a lot of times we'll use potassium nitrate, because neither the potassium nor the nitrate is going to tend to react, and it's just going to act like a conductor. You'll notice the ends are plugged so the liquid doesn't pour out, but they're porous so the ions can travel through this body. And that's what's going to allow the charge to flow. Now, when I turn all this on, let's watch what happens. So you notice the voltage we're getting here is 1.1 volts, but look carefully at what's going on. Zinc is oxidizing. The electrons are coming off, traveling through the circuit, through the wire. They're coming through the copper, and then they're causing the copper ions to be reduced onto the copper metal. Meanwhile, and you don't see this, I'll draw it, there are ions also flowing through the salt bridge. Let's see how all that looks again. Oops, question. No, it's in solution. It's dissolved in water and then put in the salt bridge. So let's watch that again. So again, the main thing I want you to notice is that the potential, the voltage I should say, is a certain value, fine. But look at the flow of electrons. Okay? So this is showing us the working of the cell. Now there's a couple of shorthand pieces of notation I want to show you. There's something called line notation, which is a kind of a nice way to represent all this. So to show all of these parts in a simple way, we could show it in the following way. Usually put the anode first, and then the cathode on this side. It's just by convention, it doesn't really matter. But so we put the oxidation reaction on this side because it's the anode side. So what we're going to show here is the zinc as the solid, Then we show a vertical line that represents a change of state, like a different phase of matter. So there's zinc in zinc solution, and I'll just show it as a net ionic form. Then we use a double line to represent the salt bridge. And then we show the reduction side, which is the cathode half cell. So here we're showing copper ions and then the copper metal here. So do you see this is just kind of a two-dimensional way of representing the same thing I drew, just that cell. So when I write it this way, I know that this is the oxidation half reaction. And so this represents the anode side, and then this is the reduction half reaction. So this represents the cathode side. Now let's zoom into this and see if we can sketch the cell in a way that makes more sense, a little bit more sense than what we have already done. So I think we left off here with this picture. And we put where the electrons are going, but let's zoom into what's going on in this salt bridge, because I think it's really important to understand what and why this is here. So let's put the salt bridge like that. Now, if we have negative charge flowing away from the anode, oops, somebody has a question. Zinc was not produced. Zinc ions were produced, right? In other words, the zinc metal was giving up electrons and becoming zinc ions in the simulation. Now, as this is happening, you're absolutely right. Zinc ions are starting to build up in here, right? That means this side is becoming more positive if nothing balances it out, because electrons are leaving and going in this direction. In the meantime, as the electrons are coming in here, they're neutralizing these copper ions, and it looks like this side's becoming more negative. If that happens, the circuit's going to shut down, because it's going to build up a potential that stops the initial potential. But the bottom line is this. We have potassium ions and nitrate ions that are free to move in solution here. This is how we maintain the balance. So what's going to happen in the salt bridge is that negative ions are going to move in this direction to balance the charge. Think about that. If electrons are leaving, which are negative, we need another negative charge to come in here to complete the flow, so that the whole solution stays neutral. By the same token, we would see the positive ions migrate in this direction to keep the charge balance within this side. In other words, what's really happening here is we have an overall flow of negative charge continuously moving in this direction. So there's a complete circuit of negative charge flow. Some of it is from the electrons in the outer part of the circuit, and some of it is from the movement of ions on the kind of internal side of the circuit. Does that make sense? That flow of the ions and why? Any questions on that?
I just don't understand how, if the potassium and the nitrate are like, I don't understand how they're balancing the charge, really.
Sure.
I don't know.
No, that's fine. Let me explain. So these are their own kind of little pile of ions that are not really part of the reaction, right? They're just there. So if we don't turn the circuit on, everything just stays the way it is. Now, if we suddenly start pumping electrons out of this side, right, because of the way the natural flow of the electricity is going, aren't we taking negative charge away from this half? And if you're pumping out negative charge, this side would start becoming very, very positive, and it would pull negative charge back in, and it would stop the flow. The whole circuit would die. But instead, we have this little pool of negative ions in the salt bridge, that can flow in and balance the total charge inside the beaker. So every time oh gosh, everything's starting to go goofy here. Every time electrons leave, negative ions come in. If electrons come in, like on the other side, on the cathode side, then positive ions come in to balance that out. So we just need the opposite charged salt bridge ion to compensate for what was gained or lost by the reaction itself. Let me kind of zoom in to make that more clear since this died anyway on me. Sorry about that. All right. So, stupid thing. Sorry, my computer just went bleh. Okay, come on, Word. Hook me up. Whatever. Let's see. No, I don't need that. Of course, that's the one I opened. I'm a dum-dum. How about this one? This one. Is any good? Whatever. That's fine. Okay, so let me kind of zoom into the salt bridge to make more sense out of it. So let's say, and it's going to be drawn in a new orientation. I think it'll be easier for you to follow. So let's do it like this. So let's say this is the salt bridge. There's potassium ions and there's nitrate ions. And it doesn't have to be these, just that as long as there's positives and negatives is all that matters. And let's say again, this is our zinc. And this is our copper. Our salt bridge has a porous, semi-permeable, whatever you want to call it, connection, so it doesn't just spill out, but the ions can flow. Okay, so now here's what's happening. We have electrons going this way, right? That means negative charge is leaving this side and entering this side, right? Those are the same two electrons, just to make an example. Well, in order for this to work, the circuit has to go all the way through. It has to go all the way around with negative charge. So what this is showing me is that these negative ions have to move this way. Because if I'm losing negative, I have to replace it. Otherwise, I lose charge balance and the whole system doesn't stay stable. And therefore, where the electrons are coming in, these positive ions have to come in to neutralize that overall charge. So the essence is that we have an overall circulation of negative charge through the circuit. Does that help, or is it still not clear?
That makes sense. I just have one more question though. So even though like the nitrate is moving to the left and the potassium is moving to the right,
Mm-hmm.
the electrons that are moving they're not coming from the nitrate, right? They're still coming from the zinc.
That's right.
Okay.
Yeah, these ions are not reacting in any way. They're just charged particles that can flow to keep the charge of the system balanced. We just need something that can move with charge here, but the electrons are not moving in here. They're moving from here to here. Yeah, you're absolutely right.
So the ions are just helping the charge to keep flowing, or
Yeah,
the ions to keep moving.
absolutely.
Or
So
the electron.
whatever. Yeah, I know what you meant. So that's the thing is, so it's, well, eventually, actually, these stay ions the whole time, and these aren't going to typically run out, but the chemical reaction is going to get used up. And that's why a battery dies, right? Eventually you use up all the chemistry and it's just a dead battery. Now, some batteries are rechargeable. That's a different story. This kind isn't. But there are rechargeable batteries, and if we have time, we'll get into that in a later lesson. But this is the essential structure of a cell and how it works. The next question then is, well, how did you know what the voltage would be? How do we figure that out? Here's the interesting part of that. So if we go to this table, which is linked on the Unit 13 website thing, where am I here? you'll notice it says standard reduction potentials. So let me open this up and just kind of explain what this is saying. So if you look at this, there's a whole bunch of net ionic half reactions that are all reduction reactions. So you see fluorine being reduced to fluoride ion. And this E represents the electrode, well, I was going to say electromotive force. Just think of it as voltage. It's the potential. So if you took physics, you know that better. But if you didn't, it's okay. Just understand that it's like the push, how hard the electrons get pushed. So if you look at this, fluorine has a very, very, very high tendency to be reduced into its fluoride form. It's very reactive too. And as you go down this list, they're in order from most reducible to least. In fact, what's interesting is as you go down, the numbers get smaller, but then you hit the hydrogen reduction and it's at 0. What a coincidence. It's not a coincidence. It was set to be 0. That's the whole point. In order to compare how strongly one atom pulls electrons compared to another, we need a reference point. So they decided to make the hydrogen reduction the reference point. They call that 0, and everything else is measured relative to how well or how not well these things can be reduced. So as you're approaching hydrogen, the reduction potential approaches 0, and if you notice when we start going further down, it becomes negative. That means simply that hydrogen is more easily reduced than the things below it. So negative doesn't mean like it doesn't get reduced. It's just a relative scale. That's all that really matters. And the main thing for us is we're going to be just taking differences between the numbers on this scale. So another way to look at this is if you look at it in the forward direction, that's a reduction. If you reverse it, it becomes an oxidation. So you can even mentally just flip everything and flip all the signs, and it becomes oxidation potentials. But we're always going to do it in the frame of reference of reduction, because it's just easier to think from one point of view every time. Now let's see what this tells us in our example. So if you remember, the half reactions we used were this one in our particular cell. So let me grab this one here and bring it over. I wish I had kept my other drawing, but whatever, I'll just start a new thing because this is probably going to puke on me anyway. Sorry. Man, this thing's running slow. It must know it's Friday. Come on. And of course now we're going to have to deal with, oh my gosh, this is so annoying. Sorry. Okay. So that's the one reduction potential. Oops. And then everything's going crazy. And the other one we need is the zinc reaction. So if I scroll around, I'll eventually find, oh, here it is. Here's the zinc reduction. Let's put that here. Well, let me put it in here. I knew that was going to happen. Oh my God. Life, why do you mock me so? Seriously now. I don't like this. Why me? I'm such a nice person. Okay, whatever. So let's understand what this is exactly saying, because this is really the crux of the argument now. If we can understand what's about to happen here, the rest becomes quite simple. Okay, so if these are both reduction potentials, I can't click it. And I'm going to write it E red for reduction. Which of these has the higher reduction potential, the copper or the zinc ion? This should be obvious, right? When I say high, yeah, I mean the more positive one, exactly. What that tells me is that if I have a choice between reducing these two, this tells me whoever is the higher meaning more positive reduction potential, is going to be the one that is reduced. That's the whole point, right? It has the stronger ability to be reduced. So even if I hadn't told you how this cell was supposed to work, you could have predicted it. You could have said, oh, okay, so this one is going to stay in this form, and its reduction potential is 0.34. But then if it's reacting with this, they can't both be reduced, right? If one's reduced, one is oxidized. So this one is going to have to be the one that's oxidized, sorry. Which means even though we have the reaction written as a reduction, in our particular case, what's really going to happen is that it's going to flip. It's going to act the other way. In our specific reaction, it's going to be the one that's oxidized. Now, I'm still going to write it as a reduction potential, and I'll show you why. Because when we put these together, these are two half reactions. When we put them together to get the overall reaction, which we saw earlier, was zinc plus copper ion makes zinc ion plus copper, we can find what's called E cell, the potential for this entire cell once we throw it together. And again, the easiest way to do this is to just subtract, take the difference between the reduction potentials in the following manner. You're always going to do the cathode one, meaning the one that's actually reduced, minus the anode one. Basically, the more positive one by the more negative one. Okay? I shouldn't say plus and minus because that'll confuse you because sometimes they're both plus and sometimes, never mind. So all I'm saying is that what we could have predicted is that in this case, just by looking at these numbers, that the cell potential, the overall voltage that we could get out of this cell would have been 0.34 minus negative 0.76, which is about 1.1 volts. And that's exactly what we saw. In the lab that they showed on the YouTube video, it was pretty close to 1.08. In this case, the Daniel cell that we showed on our simulation, we saw that 1.1 volts. And that's how we knew it would be 1.1 volts based on this. And that's really the whole story from one cell's point of view. The only thing I should point out is that this potential is based on standard conditions. So this table that I'm basing these numbers on are making the following assumptions. That all the concentrations are 1 molar solutions, that the temperature is 25 degrees Celsius, things like that. Now, will we learn what happens at non-standard conditions? Eventually. Not today. But let's try a follow-up problem. So I'm going to propose a cell, and I want you guys to see if you can predict the voltage and do the whole thing that we just talked about by looking at this table. And let's see, let's change the thing. Let's use silver and copper. So let's say we want to do a copper-silver cell. If that's the case, and I'll write the initial reaction so we have something to go by. So let's build a silver copper cell. And let's figure out everything. The anode, the cathode, what's oxidized, what's reduced, the voltage, the salt bridge. Let's put it all together, okay? So let's see if we can pick the reactions we think it's based on first. So we're looking for a reduction potential involving silver. Here's one, but this is for +2 to +1, and we don't want that. Keep looking, that's gold. Silver, here. So let's write this first. So let's see the reduction for silver here and its potential. Sorry, keep bopping things around on you. we find that this reduction potential shows us that when silver is reduced relative to our scale here, the reduction potential is positive 0.8. A moment ago, we saw the copper. We were going to do copper 2, not this copper 1. So it's really important you know which reaction you're doing, obviously. So for the copper, let's use this, again, copper 2 reduction. And this one has a reduction potential of 0.34. So my first question, once we have that data, is can we tell which one of these is going to be oxidized and which one's going to be reduced? Can we tell which one goes where?
The silver will be reduced and the copper will be oxidized.
Good. So this will be the reduction reaction. This is going to be the oxidation in our particular case. Okay. Now if that's true, we should be able to start building a cell that reflects this. Because on the one side of the cell, actually I don't have to draw it, we can just actually build it on the simulation. On the one side, now which one is positive and negative again? I forget. What should I connect to the positive side?
Silver.
Because that's the, oh wait, is that right? Let's see. If I put the silver here, whoops, and then I have to put silver solution, that means you're telling me to put the copper on this side? And copper solution.
Is that wrong?
I don't know, let's find out.
Oh, okay.
So before we actually turn it on and get it going, because this is not the right number, I just didn't, I don't know if I was supposed to reset it, but I think it'll change when I turn it on. But let's see if we can figure out what the calculation would have been. Now here's a very important thing. This is one of those rare cases where if we use a multiplier, it does not change the potential. So you can see that to balance this equation, I would have to double all these numbers to get 2 electrons for both. It does not affect the voltage. So the potential difference is independent of the coefficients. And the reason why, and let me give you an analogy. If you have a very steep hill that has a certain width, a ball will roll down with a certain speed, right, based on the steepness of the hill. If I now expand the width of that hill, the balls don't go any faster. There's just more room for more balls to roll down. The potential is the steepness. And that's why no matter what I do to, like if I multiply, if I triple, if I quadruple these numbers, it doesn't change the potential. So this is that kind of one weird place where if we multiply the equation, we don't change the number. So even though I have to double this, this is still a potential of 0.8 volts. So based on that, can you tell me what the cell potential should be? Even without writing it or like sketching it out. From what we said, all we have to do is what? To get the cell potential.
Subtract the one that's oxidized from the one that's reduction.
Yeah. And I see somebody said 0.46 volts. We can test that now by turning this on. Voila. It looks good. So according to this, our copper is being oxidized. That's our anode. That's the negative terminal. It's losing electrons because the silver has the higher potential for reduction. It's pulling the electrons across and the silver is getting reduced. So it turns out you were right, Imelda. Does that all make sense so far? So that's really what this lesson was meant to introduce you to. Not only can we, well, let's do one more thing on this. Let's draw the line notation for this. So to draw the line notation, again, we go oxidation first. So it looks like that would be our copper, which is our electrode. In this case, it's our anode, and it's our negative terminal. And this is then separated by a difference in state of matter from the copper solution. So again, I'll just show the net ionic form. Then there's the salt bridge through which the ions travel to keep charge balanced in the beakers. And then we have the reduction side, which is the silver ions in solution, and then the silver metal, which is the other electrode, in this case, the cathode, which is the positive terminal on our thingamabobber. So again, this is just another way to represent the same structure. One last thing that would be of interest to note, that as we watch this process go, the anode, the one where the oxidation is happening, is going to shrink because the metal is dissolving. And the cathode, where the metal is being reduced, is going to get heavier because we're actually plating or attaching neutral metallic atoms to this piece. So that question comes up sometimes, like, how will the mass change over time? And that's based on, is it dissolving or is it plating on? So obviously this is just a very gross introduction to these concepts. In terms of what kind of practice problems I give here, that really starts in this second section of these problem sets, if you want to look at them. So this is just asking you to compare who can oxidize or reduce who by looking at this table. And then this next question again asks you basically to do what we just did. If you were putting these together, how would you build the cell? And it asks you to identify specific things about the cell. So there's some practice like that, and more of the same. Now, an interesting thing we should note is what happens if we build a cell and there's no natural solid electrode. Like sometimes you're going to have solutions with solutions, and there's no like solid metal piece. For example, if you look at, sorry, it's like too many. That's the wrong one. Wait. Oh, if you look at this, like look at this reaction. This half reaction is all solution. There's no solids. So what do I stick in there as my electrode? So that's an important side note. Let's put it in there. If there's no natural electrode to use, and by natural I mean one of the components is already a solid, typically you use an inert metal, and the most common things that would be used would be like platinum. So if you see like platinum sticking in a solution, that's acting as an electrode because it's not reacting. It's not going to do anything but be a conductor for you. Sometimes you might also use, other than a metal, graphite, which is just carbon, like a pencil lead, because it's a decent conductor. And again, it's not going to react with your solutions. So just in case, if you see a problem, and we will eventually, that's why that's there. It's because we're not, in the natural redox reaction, we're not using a solid. And that's why we need some other material to act as the electrode. Miriam, you asked why would the silver metal increase? Because as the reaction is progressing, what's happening is that, see these silver ions? Look at where they're going. They're being reduced onto the electrode. And so they're literally attaching and sticking to the metal. And so the metal is growing on that side because it's pulling stuff out of the water and getting it attached to it. All right, any questions overall about this lesson? Feel okay?
I have a question.
Sure.
How do you pick what salt to use in your salt bridge, or does it just have to be a negative and a positive?
Yeah, the main things is you want something that's not going to be easy to oxidize or reduce because you don't want it to interfere. So typically nitrates are going to be super already oxidized, so they're not going to oxidize anymore. In fact, I don't think you'll find nitrate on here anywhere. And then these metal ions way down here, look at how negative their reduction potentials are. So they're typically not going to interfere as well. You don't usually have to pick that. It's almost always potassium nitrate or sodium sulfate or something like that.
Okay, thank you.
Sure. Anything else?
I have a question.
Yeah.
So at the when you were writing out the equations, how come you chose those? So like you said that you doubled
Oh,
when you're talking
these?
about you doubled it and it doesn't affect it. Wasn't there an equation already on that sheet that was doubled already?
You know, and again, you have to kind of have some information to start from, right? Like I just picked those because I knew those are the ones in the simulation. But could I have used this or could I have used that? We can pretty much build any cell combination we want. So it's really just a question of how the question is phrased. So like if you look at the problems that I put up for you, it's giving you the reaction already. So you can already pick the parts apart. See what I'm saying? It's like, here's the reaction. So you can go back to the list of reduction potentials and find the right things that are going to match. But yeah, in my case, I just picked it to make an example. And next time what I'll probably do with you in this session is that I would probably go over some of these with you just to kind of review all the stuff we just learned. Because again, we don't have to rush this because the last portion of this unit is dependent on something we're going to have to do during class anyway, so the timing is going to be kind of interesting. The previous video was just everything on this whole extra sessions is always going to be on this link. And this link, meaning this little syllabus, is on our main website where it says here extra sessions. So if you go to Canvas and hit extra sessions, you bring up that document. Yeah, everything that we've done is linked there. Okay, well, thank you guys for coming, and we'll see you next time. Have a nice weekend.
Thank you.
Take care.
Thank you, Mr. Kritzos. Bye.
Bye-bye.
Thank you. Have a great weekend.
You too. Thanks.